Hi everyone, welcome to lecture 32 of your electric circuit class. And lecture 32 is about power quantities. The objectives of this lecture: the first objective is to determine the average power in terms of RMS values. The second objective is to define and determine the apparent power. The third objective is to define and determine the power factor. And finally, define and determine the reactive power. So we have new terms, that is apparent power, power factor, and reactive power. So we will start with the average power in terms of RMS values. So recall that our P is equal to VRMS IRMS cosine of theta V minus theta I, and that is in watts. So this is the formula for average power when we are using RMS values. So we can say also our P is equal to VRMS squared over R, and that is in watts. In this case, this VRMS, that is the voltage across the resistance. What we mean by that, if I have, for example, this impedance, and then I have VRMS here, then that is not this VRMS. So I need the voltage here. Okay, not this one. I need this one across only the resistance. Or we can use that P is equal to IRMS squared times R. So in this case, when we have, for example, an impedance like this, then this current, which is IRMS flowing here, and this is R, JXL, then this current is flowing through the resistance. So we can use this to get our average power, because that current is flowing through the resistance and the reactance, so it is the same current. So we can use the current squared times R, but we take only the magnitude of the phasor IRMS. We do have a term called power factor. Power factor, so recall the average power which is P is equal to VRMS IRMS cosine of theta V minus theta I. So let us take some notes here. So some notes on this equation. The first note, that we do have apparent power. Our apparent power is the product of RMS values of voltage and current, and it is measured in volt ampere, which is just simply VA. And the apparent power, we give it a letter S. So our S is equal VRMS times IRMS. So this here is apparent power. So the product of VRMS and IRMS is called apparent power. And the unit here is volt ampere, because we are multiplying voltage by current, so volt ampere. The second note, the power factor. The power factor is defined as the cosine of the phase angle difference between voltage and current. That means our power factor is equal to cosine of theta V minus theta I. So this over here, power factor. Then we have the power factor angle. So that is the phase angle difference between voltage and current. So the angle of the power factor is equal to the angle of theta V minus theta I. Power factor angle is equal to impedance angle. Then power factor varies between 0 and 1. That means our power factor is equal to greater than or equal 0 and less than or equal 1. So if you get a power factor of 1.2 or 1.5 or negative something, that is wrong. So all the time that it will vary between 2 values. The two extreme values are 0 and 1. So based on that, if power factor is equal to 1, which is in this case we call it unity, then our theta v minus theta I is equal to 0, because cosine 0 is 1. And from that, this over here is a pure resistive load, only resistance involved. The second case, that if we have the power factor is equal to 0, that means we will have theta v minus theta I is equal to plus or minus 90 degrees. And from that, if we have a plus 90 degrees or minus 90 degrees, we call it a pure reactive load. When we are saying that a pure reactive load, that means the element involved is only L or only C. No R involved in that. So under this here, we do have the first case, that if theta V minus theta I is equal to positive 90 degrees, then we can say that is a pure inductive load. And the second case, that if theta V minus theta I is equal to negative 90 degrees, then we can say a pure capacitive load. Are these going the other way around? So if I have theta V is here and theta I is here, then I lag, which is a pure inductive. If I have, so this is V, theta V is here, and theta I is here. So theta V minus theta I, so in this case theta I is behind, so pure inductive load. And the second case over here, if I have this over here to be the I and over here the V, then our V is behind, which means that I is leading, so we have pure capacitive. So over here we have V, phasor V, and over here phasor I. And the angle here is 90 degrees, exactly 90 degrees. So that is why we are saying a pure. And then if PF is greater than 0 and less than 1, so we will have leading power factor if I leads V, and we call that lagging power factor if I lags V. So from now on, when we are, let me write that as a note, always power factor leading or lagging, we are referring to the current leading or lagging. So for example, if I have V is equal to 10 with angle, let's say 50 degrees, and I have I is equal to 2 with angle, let's say 0 degree, then in this case, I is behind, then we will say that if I change this to, let's say 45 degrees, so I will know the value of our cosine. So over here that our power factor is equal to cosine of theta v minus theta I, and that is cosine of 45 degrees minus 0, and that is cosine of 45 degrees, and this is equal to 0.707. However, now I have to put this power factor leading or lagging, because if we put power factor is equal 0.707, that is incomplete answer. So we have to put after that leading or lagging. In this case, if you look at it, our I is lagging the voltage, because if I want to present this as a phasor diagram, I have the current here to be 2 with angle 0, and then I have the V over here, which is, let's say, 10 with angle 45 degrees. So the difference here is 45 degrees. So I is behind, then we will say lagging. So all the time that this here lagging or leading, that goes to the current, okay? Correspond to current all the time. So now we have our power factor, our average power, our apparent power known. Now we have what we call the reactive power. Reactive power can be defined as is the portion of power that flows into the load, then back out. Usually the reactive power is measured in volt ampere reactive. So you can use var or uppercase var, and this is like it is present only when L or C are involved in the circuit. So reactive power can be written as Q is equal to 1/2 Vm Im sine of theta V minus theta I, and that is volt ampere reactive. Or in RMS quantities, that is VRMS, IRMS, sine of theta V minus theta I. Or we can say that our Q is equal to IRMS squared times X, or Q is equal to VRMS squared over X. However, that this VRMS, the voltage across the X. So again, if I have something like this is our JXL, this is R, then over here that I have to get this, the magnitude of this voltage across the reactance, and substitute it over here. However, that for this Q, which is IRMS squared times X, because the current flowing here, which is IRMS, let's say, it is the same current flowing through the R and flowing through the X, then we can use IRMS squared X. So that is very important. So now let us go over an example to show you the application of these equations. Given the voltage across a load impedance as V is equal to 120 with angle 30 degrees, and that is in volts, and the current through it as I is equal to 4 with angle 10 degrees, that is in ampere. We need to determine the following. For letter A, the RMS value of the voltage, B, the RMS value of the current, C, the apparent power, D, the power factor, E, the load impedance, F, the average power absorbed by the load impedance, and finally the reactive power of the load impedance. So this is our solution here. So our voltage and current we did not say that they are an RMS, which means that we are using the amplitudes, like right away the phasor from the cosine waveform right away to phasors. So the first one here, our RMS value of the voltage, that is V RMS, is equal to the phasor V divided by radical of 2, and that is equal to 120 with angle 30 degrees divided by square root of 2, which is equal to 84.85 with angle 30 degrees, and that is in volts. For letter B, our IRMS is equal to phasor I divided by radical of 2, and that is equal to 4 with angle 10 degrees divided by square root of 2, which is equal to 2.83 with angle 10 degrees, and that is in ampere. For letter C, we need the apparent power. So apparent power, that is S, is equal to the magnitude of VRMS times the magnitude of IRMS, and that is equal to 84.85 multiplied by 2.83, and that is equal to 240.126, and the unit is volt ampere. For letter D, we are looking at the power factor. So our power factor is equal to cosine of theta V minus theta I. And in this case, that is cosine of theta V is 30 degrees minus, and theta I is 10 degrees. From that, that is equal to cosine of 20 degrees, which is equal to 0.94. So our power factor is 0.94. However, that this is not a complete answer. We have to indicate whether it is leading or lagging. Excuse me. So if you look at the voltage angle and the current angle, we know that the voltage is leading the current, which means that our current is lagging. So we can say 0.94 lagging. And why it is lagging? This is because we said that all the time the power factor, whether it is leading or lagging, you are talking about the current. So this over here, because I lags V. And then for letter E, we are looking for the load impedance. So our load impedance, that is ZL, is equal to phasor V over phasor I, and that is 120 with angle 30 degrees divided by 4 with angle 10 degrees, and that is equal to 120. That is angle 30. We bring this angle to the top, it will become minus 10 because we need to flip the sign, divided by 4, and that will be 30 with an angle of 20 degrees, and this is equal to 28.19 plus J 10.26 ohm. All the time that we like to have our impedance to be in rectangular form. We have said that voltage and current in polar form, however that the impedance have to be in rectangular form. The reason behind that, because when it is in rectangular form, we will know the value of the R and the value of the X. And of course that we can use to find the load impedance, we can use the RMS voltage and RMS current. That will end up with the same answer. For letter F, we need the average power, that is P, which is equal to, you can use 1/2 Vm Im cosine of theta V minus theta I, and that is equal to 1/2 times 120 times 4, and then cosine of 30 minus 10, and that is equal to 225 watts. Or you can use P as VRMS IRMS cosine of theta V minus theta I, and that is equal to 84.85 times 2.83 cosine of 30 minus 10, and that is 225 watts. Or you can use P is equal to IRMS squared times R, and in this case that is 2.83 squared times, our R came out to be 28.19, and that is equal to 225 watts. And here note, we cannot use P is equal to VRMS squared over R, because the given VRMS is the voltage across the impedance, not across the resistance. And then the last part, which is G, that is the reactive power. So our Q is equal to, you can use 1/2 Vm Im sine of theta V minus theta I, and that is 1/2 times 120 times 4 sine of 30 minus 10, and that will be 82.17 volt ampere reactive. Or you can use Q is equal to VRMS IRMS sine of theta V minus theta I, and in this case that is equal to 84.85 times 2.83 sine of 30 minus 10, that will be 82.17 volt ampere reactive. Or you can use Q is equal to IRMS squared times X, and that is equal to 2.83 squared times our X came out to be what here? This is our X over here, which is 10.26. And that is equal to 82.17 volt ampere reactive. So over here again, we cannot use VRMS squared over X, because the given VRMS is across the whole impedance, not only across the reactance. By this, our lecture is done for today. As long as you know the following, you will be in good shape. That the power factor is cosine of theta V minus theta I, and always indicate leading or lagging, and that is based on current, if that is leading or lagging. We have said that our S, which is the apparent power, that is VRMS times IRMS. So the product of the RMS values of voltage and current, and the unit is volt ampere. The third thing, that our Q, that is our reactive power, and that is equal to VRMS IRMS sine. This is sine of theta V minus theta I, because if it is cosine, then that is the power, which is the average power, and that is in volt ampere reactive. So all the time that our power triangle will be very helpful. So if we have this as our real power P in watts, this over here is our Q, that is a Q in volt ampere reactive. Then this is over here is our S, and this is the power factor angle, which is theta, that is theta V minus theta I. So in this case, this present for us inductive load, inductive, because this is the orientation. Our Q is positive, then that is inductive. If it is like this, this is P, this is a Q, and this is our S, and this is our theta V minus theta I, that angle. So in this case over here, if you look at the Q is going down, so it is negative, that means this is capacitive load. And forget that, guys. By this, I think that you will be in good shape in this lecture, and this is our homework for this presented lecture. Thank you for watching.